Okay, thank you so much. I guess you can imagine what I'm going to be talking about today. Let's talk a little bit about geochronology, and we can go ahead and cue up the first slides. Okay, I'll just start off by saying thank you so much for being the recipient of the 2024 Emile Argand Medal from the International Union of Geological Sciences. This is an auspicious time to receive this medal 2024. It was exactly 100 years ago that Emile Argand published his masterpiece study, The Tectonic Synthesis of the Asian Continent. He also prepared a geological map of the Asian continent, which was revolutionary. He was really the first person to try to do this after the new world of continental drift was discovered by Alfred Wegener in 1915. And so he is really one of the first geologists to try to take this new world of continental drift mobility and put that into continental geology. And he did this in a most masterful way for the continent of Asia. And perhaps more important than that, he figured out how we would do these types of studies, what sort of geological measurements and observations we would make, how you would plug these into regional tectonic reconstructions to say something about the evolution of something as complicated as a continent, as the Asian continent. So here's Emile Argand here, the man on the medal. I'm going to start off kind of with my citation just to acknowledge my heroes, my mentors, the people who have enabled me to have this most amazing, wonderful career in earth sciences. Across the top are the people who have helped me learn how to do uranium-lead geochronology, which we'll be talking about primarily today. My PhD advisor in the upper left there, Jason Salibi and Jim Mattinson, were the people who taught me uranium-lead geochronology as a graduate student at Caltech. When I was hired by the University of Arizona in 1985, I was there with John Patchett and Joaquin Ruiz, eminent geochemists who were very generous in sharing their lab, their expertise, especially their mass spectrometers with me, so that I could set up my lab and begin my research career. And most recently, I really need to acknowledge the tremendous work of Mark Pekka, our lab manager for the last 20 years or so, and a new person that we just hired to be the co-director of our lab, Mauricio Ibanez Mejia. He's an up-and-coming, just very creative, very intelligent scientist, and I think you're going to be hearing a lot from Mauricio in the future. And in the world of sedimentary geology, I owe a big debt of gratitude to Bill Dickinson, of course, one of the heroes of sedimentary geology and plate tectonics. I had the honor of being a colleague with Bill Dickinson for much of the early part of my career, and also Pete DeSalle, another sort of master stratigraphy sedimentology person. And Bill and Pete were really essential in helping me try to understand how we apply geochronology to sedimentary rocks and sedimentary processes. And then, of course, I need to acknowledge the tremendous support system of my family. My wife, Jennifer, and my son, Jim, are down front here. My daughters, Aleda and Taya, are back in the US, and of course, their support has been just instrumental in allowing me to do the work that I've done in my career. And to them, I would just apologize for missing so many dinners and weekends. I'm sorry, I was in the lab doing my research. So let's jump in and talk a little bit about how uranium-lead geochronology works. This kind of will help you understand why I think this is something that's worth discussing. The technique works with the mineral zircon. In the upper right there, you can see gem-quality zircons. Unfortunately, we don't get to analyze many that look like that. We analyze the ones a little bit down there. And what you need to realize is that these are all very tiny minerals. The ones we analyze are pretty much too small to see with the naked eye. This is all micro-analysis. Zircon is a great mineral to do this because it contains lots of uranium. We're going to be using the uranium-lead decay system, so lots of the parent, uranium, not very much of the daughter, lead, and so this allows this to be a very good chronometer. Zircon is a very common mineral in continental crust, ZrSiO4, a formula that's very similar to quartz, SiO2, so pretty much any rock that contains quartz is going to have the mineral zircon, so we can use this for geochronology. So, for example, the slides on the left here, plutonic rocks, if they contain quartz, they would contain zircons. Volcanic rocks, we can date eruptions of volcanic material. We can do metamorphic geochronology by extracting zircons from metamorphic rocks. And today we're going to talk about the application of geochronology to sedimentary rocks. So this Zircon decay system here is a very powerful tool. There are two different isotopes of uranium, 238 and 235. They decay to different isotopes of lead, 206 and 207. And these are great for telling time. It's kind of like you have two watches on your arm, and what you can do is compare the results of both of those. If they're in agreement, then you know you have a reliable age. If they're different, then you know that there are some complexities in the system. Another great aspect of this decay system is that they have the perfect half-life to study Earth history. Uranium-238 half-life of 4.5 billion years. Uranium-235 half-life of 700 million years. This is exactly the right playing field to do reconstructions of Earth history for the last 4.5 billion years. Okay, so let's look at this curve. This is what I refer to when I talk about the Detrital Zircon revolution, the DZ revolution. I'll use that term. What I've done here is I've shown the publications that have come out per year between 1970 and 2020 that report geochronologic information. And the different color bars on there represent the different chronometers that have classically been used in Earth science: uranium, thorium, helium, SMND, rubidium, strontium, argon, argon. In the yellow curve is the application of the uranium-lead system to magmatic processes, volcanic rocks, metamorphic rocks. And check out the red curve. The red curve is the number of publications per year that report uranium-lead geochronologic data from detrital zircons. So this is what I refer to as this revolutionary phase. I think in the last 20 years, we're seeing this just exponential growth, this explosion of interest in this technique. And that's what I want to talk a little bit about today, is what the drivers are for this revolution in geochronology. I think that there are three different drivers that have caused this explosion of interest and application in geochronology. And I'll take you through kind of a storybook of each of these three. We're going to talk about the instruments that have made this possible. We'll talk about new applications that have made this possible. And number three is kind of a surprise. This is all driven by opening of the doors of our laboratories to allow people to come into our labs and generate geochronologic information, even if they're not trained officially as geochronologists. This is a technique that all geologists are going to be able to do. So let's dive in. We'll talk part one here is about instruments. On the left here is the instrument that I was able to use as a graduate student at Caltech. These are very cool, historic instruments. This is the instrument that Claire Patterson used when he first determined the age of the Earth. This is the instrument that Jerry Wasserberg used, instruments like these at Caltech, when they first determined the age of the moon from the Apollo mission samples. And I was very fortunate as a graduate student to be able to learn from these researchers and use these instruments. They were kind of interesting instruments. Nowadays, you don't see these so much. These were handmade. They were soldered and they were welded together and wired together by these scientists. They were kind of one-off instruments that were designed to do particular things. And they were a very powerful tool, but for the kind of research that I was interested in doing, boy, were they slow. It would take 5 days to do an individual age determination. You would take the zircons from your sample, you would dissolve them in a clean lab, and this is kind of an interesting process. It takes high temperatures and high pressures of hydrofluoric acid, not a very friendly substance. You would dissolve the zircons, then you would separate the uranium and lead from the other elements, and then finally you would go into the mass spectrometer room, load them up onto the machines, and there you would be for 5 days trying to generate a single uranium-lead age. So the world changed in the mid-80s. Companies first came on the scene producing these mass spectrometers, and this was a great thing because many different labs could now have the same instruments. Instead of having one-off instruments, we were all using the same machines. They also had some real great advantages to them. They had multiple collectors within them, so you could analyze all the different isotopes of uranium and lead at the same time. So we could go faster. We could do 3 hours per age was the rate that I was able to do as an early career professor at the University of Arizona. This seemed like we were going at light speed from 5 days to go down to 3 hours. That was super exciting. Of course, at the same time, ion probes were being developed. Korea Geological Survey has one of these most beautiful instruments. These are the most powerful instruments in geochronology. They are the main instrument that was used for detrital zircon geochronology early on. Some of the earliest work on the earliest, oldest zircons on Earth were done with these ion probes. But they have not been routinely used for this type of application because they're expensive to acquire and to maintain, and so there's not that many of these instruments available. But they're pretty fast. You could do an individual age within about 15 minutes, and so these instruments were really instrumental in early applications of this technique. The world really changed in the late 90s. The very late 90s saw the advent of this instrument here. This is a laser ablation ICP-MS instrument. It was made in a factory, and so many of these were available. We were very fortunate at the University of Arizona to get one of the first of these in North America. When we first got this machine, I thought, I don't think we're going to be able to do uranium-lead geochronology with this instrument. I was skeptical. I thought that we would be using the traditional techniques. And so I spent about 2 years trying to learn how to do uranium-lead geochronology with this instrument. And at the end of that time, I was convinced this really is a great technology. This is a great tool to do geochronology. And one of the main advantages is that you don't need to dissolve the zircon material to do the geochronology. So upper left is just maybe 100 zircon grains from a sample. What we're able to do is polish down the surface of those zircon grains. With the laser system, we ablate down into that material. That ejecta, the ablated material that comes out of the laser pit, then goes into the mass spectrometer through the plasma source on the middle left there. High ionization potential, so we're seeing lots of charged atoms of uranium and lead. They go into the mass spectrometer, and then with the multiple collectors, we can determine these uranium-lead isotope ratios very rapidly. So this was a kind of a groundbreaking development, the availability of these kinds of machines, because you did not need to dissolve these zircons. You didn't need to go into the clean lab and work with these very dangerous materials. They were not very expensive, and so they were rapidly disseminating out into the community. I would guess that most of you are at universities that now have laser ablation ICP-MS instruments, and so there's a lot of universities that are doing these kinds of analyses now. One of the interesting things about these instruments is that they actually have a hole on one end where the sample comes in, the round disc there, that's actually a 1 millimeter diameter hole. And on the left side, that's an atmosphere. That's where the ionization is taking place in the plasma. Then it gets pulled into the mass spectrometer where it's at a high vacuum, and you can do the isotope analyses. Because of that hole in the end of the instrument, there's a high background counts of the different uranium and lead atoms. And so what that means for us as analysts is that we want to put a lot of uranium and a lot of lead into those collectors to raise the signal up above that background so we can measure the intensity a little bit better. And so people ask, why is it that we can go so fast with laser ablation ICP-MS? And the answer is we have to, because these instruments have a hole on one end. They're pulling a lot of this background material in, so we have to go fast, generate lots of counts of uranium and lead. So with our first application of these new instruments, we were able to go much faster, 3 minutes per age. That's going pretty fast compared to early life as a graduate student and an early career professor. And then, of course, these instruments became a little bit better in the 2000s and 2010s. New lasers and new mass spectrometers became available. In the 2000s, we were able to do each individual age determination in about 30 seconds. And more recently, mostly through software developments, we've been able to go as fast as about 3 seconds per age. So I've shown that change in the rate of acquisition on this diagram here. The red line shows basically how in the 80s it would take 5 days to do an analysis, and then 3 hours, 3 minutes, 30 seconds, and now going at a rate of 3 seconds. This is kind of an explosion in the rate of being able to do this geochronology. Just for an interesting comparison, I've also shown on here Moore's law. You know what Moore's law is, right? This is the number of transistors that you can put on an integrated circuit board. And of course, that technology has been changing and developing very rapidly. And it's interesting that our ability to do geochronology is kind of advancing at the same rate that we're able to put transistors on a circuit board. And yet geochronology requires Teflon and lead-205 and multi-collectors, laser ablation systems, plasma. All these different technologies come together. And maybe what we're seeing here is just sort of the pace of human creativity, human ingenuity, being able to identify problems and find solutions to them to improve how we do our science. So this is part one of the revolution, I think, is the development of these new instruments that allow us to go much, much faster for doing this kind of work. Part two is applying this type of geochronology to the sedimentary archive. Of course, much of the crust of the Earth consists of igneous rocks, granites, and volcanic rocks and metamorphic rocks. But of course, there's a veneer of sedimentary cover that blankets much of the surface of the Earth. And this sedimentary archive goes all the way back to the earliest parts of Earth history. So we have this amazing sedimentary archive that we can do with geochronology. That was not done traditionally. When I started doing this work in the 80s, geochronology was done mostly to date rocks. So for example, you go to Yosemite, you take a sample of a granite body, extract the zircons from that granite. You might analyze 10 different crystals from that granite, and what you would come up with is the age of crystallization of that magma into the granite body. You would date that rock. Or you'd go to an area with layered volcanic rocks, and you would collect samples of the volcanic rocks, date the zircons, and you would get the eruption age of that volcanic material. You're dating that rock. Or lower left, you could date zircons that come from metamorphic rocks, and you would be able to talk about the age of metamorphism of that rock. But that's not the case with sedimentary rocks, right? Sedimentary rocks, like a sandstone, consists of individual sand grains that may have come from many different places, and they're now found within this sandstone layer. And so the question for you is, do you think the age of the sandstone is older than the zircons, or do you think it's younger than the zircons? I'm going to be Professor Gehrels here and ask a question. You think the sandstone is older than the zircons or younger than the zircons? How many people think it's older than the zircons? How many people think it's younger? Yeah, of course, right? The zircons have to be there first, and then you can accumulate them in this sandstone. So people were asking when I gave my first detrital zircon talks in 1987, I guess it was, say, George, what are you doing? You're not dating a rock. You're dating these loose crystals in this sandstone. They have nothing to do with that rock. They have nothing to do with each other. You don't even know where they came from. So why does that age tell you anything? You're not dating a rock. So it took me a while to come up with a good answer for that, but I think I did, and I'd like to share that with you. Why is it that we do this detrital zircon geochronology, looking at ages from sedimentary rocks? So I'm going to talk about 3 different applications of this technique. One of them is provenance, and so let's go on a little field trip up to Alaska. We'll go along this beautiful river here and take some sand. We'll extract the zircons from that sand, analyze those different zircon crystals. If we know something about the ages of rocks in the adjacent mountain ranges, what we can do is match up the ages of the crystals with the ages of those source rocks in the mountain ranges. And you can talk about where that sediment came from. How much sediment came from the mountain range lower left? How much in the far background? How much on the right? You can do kind of quantitative budgets of sediment transport by doing these different analyses. This is sort of the origin of the source to sink approach to doing sedimentary processes that has become so powerful and so popular. To do this, of course, you want to do lots of different analyses, right? You couldn't do just 10 crystals. Do you think you could do 100 crystals and really characterize the ages of zircons in this river sediment? Maybe you'd want to do a little bit more than that just to get all the different age populations in that material. So provenance is one of the main applications of this technique. You can also do this on older rocks, the Grand Canyon here, one of my favorite places in northern Arizona. The beautiful sandstone layers that we see that rim the Grand Canyon that give it its beautiful scenery also are largely sandstones, and so we've done detrital zircon geochronology from these old sandstones. They're Permian in age, 280 million years old. And to our great surprise, the ages of these zircons tell us that they were not derived from any nearby mountain range. Most of the sediment in these layers in the Grand Canyon actually came from the Appalachian Mountains. I think if you want to study the history of the Appalachian Mountains in the eastern part of North America, you should go to the Grand Canyon, because that's where all the sediment ended up that was being eroded from the Appalachians as it was forming, being uplifted and eroded. So we can talk about the provenance of sediment from ancient sedimentary layers. And of course, we can do this all the way back through Earth history. We can take earliest Archean 4.0 billion-year-old sediments, and we can look at the zircons in those sediments and talk about their provenance. So this is not limited by age. We can do this anywhere in geological time. Second main application of this technique is what I would refer to as source terrain characterization. Let's go on another field trip to the Gamberts of, we can't go there actually because the Gamberts of mountains are not exposed. This is the largest mountain range on Earth that has never been seen, has never been studied because it's entirely beneath the Antarctic ice sheet. But we know a little bit about the rocks that are in the gamberts of mountains because the glaciers in Antarctica, the ice sheet has carried sediment from the gamberts of mountains out to Pritz Bay. We've analyzed samples of those detrital zircons that were carried from the gamberts of mountains, and we can use those to talk about the geology of what's in that mountain range underneath the ice cover. Here's a really famous one. This is one that kind of started the detrital zircon revolution, is looking at Gehrels quartzite. You may have heard of this unit. It's a spectacular unit in Western Australia, and it's such an important unit because it contains the oldest zircons on Earth. So lower right, those are some of the zircons from the Gehrels quartzite. Some of those go all the way back to 4.4 billion years old. This is the oldest material on planet Earth. The oldest rocks we know of go back to about 4.0 billion. In the Gehrels zircons, we have a small proportion, but a measurable number of grains that range from 4.0 to about 4.4. This is actually the only record that we have of what was happening on planet Earth for the first 500 million years of Earth history. For the first 20% of Earth history, all that we know about our planet comes from those little zircon crystals. So what an amazing record we have. We can characterize the source terrain, planet Earth, what was happening on planet Earth for the first 500 million years. That record is preserved in those Gehrels zircons. So do you think that we've analyzed lots of detrital zircons from Gehrels quartzite? Yes, many people have spent their careers doing analyses. We have millions of analyses from Gehrels zircons. So we actually can talk a lot about ages of magmatism, metamorphism was taking place in this earliest phase of Earth history. So that was application number 2. Application number 3 here is talking about the maximum depositional age of these zircons. So let's go on a little field trip to northern Arizona. We're going to collect some samples from the sandstone layers on the left. We'll extract out those zircons. We'll take them to our lab. We'll analyze those detrital zircons, and we'll get the age distribution that you see on the right. Those red bars basically represent the numbers of ages, of different age of those detrital zircons. And what we can say, as you have helped me figure out already, is that the sandstone must be younger than those youngest zircons, right? And so this is turning out to be a very powerful tool. There are thousands of papers written now per year with people doing max depot age analyses of sandstones. These sandstones go all the way back through Earth history, back to the earliest rocks like we saw with Gehrels. You can do this for all of Earth history. You can do this for any sediment that contains quartz, and so we have a really rich archive, a sedimentary archive that we can do with these different techniques. As I mentioned a couple of times, this requires lots and lots of analyses. Okay, I'm going to wrap up here just quickly. So in this sample, we've analyzed 2,000 grains from that sample, and you can see the age distribution on the bottom. What would happen if you would only do 100 analyses from that same sample? Well, the upper gray bar shows that you might miss actually some of these really important age components within that sample. You might entirely miss that 100 million year old population, not be able to do this max depot age. So we need hundreds, maybe even thousands of analyses. Laser ablation ICP-MS is perfect for doing this. The third main driver of this revolution, I think, is the involvement of people who are not geochronologists, because we do not need to go into a clean room and work with these acids in this very clean environment. Many people can come into our laboratory and do this type of geochronologic analyses. So here's just a picture of some people who have come to our lab, not necessarily geochronologists. We can put them in front of the mass spectrometers. Within about an hour, they're generating data. Within about 2 hours, they're making plots talking about provenance and max depot age from their samples. So this is kind of a revolutionary thing, that now geochronology can be done by people who are not formally trained as geochronologists. Here's just a few pictures of what it looks like in our laboratory at various times. You can see people sitting in front of the mass spectrometers. This is so much fun. You press the fire button. 15 seconds later, you get an age, and this is discovery science. Nobody has ever gotten that age before. You're learning something new about magmatic processes or sediment distribution or depot age of these zircons. The students in the lower right, I think I would refer to them as students that maybe have got zircon fever. I warn people when they come into the lab that this is very contagious. There is no known cure. There are no vaccinations. People get so excited about doing zircon geochronology. They are very excited about what they're doing. So here are the 3 different drivers kind of shown on that same plot. We're going faster, faster, faster. People are generating larger and larger data sets, and we're seeing this incredible number of publications coming out per year with this geochronologic information. So that's kind of the perspective from geochronology, from a geochronologist. That's what I was kind of describe as the DZ revolution from a geochronologist. But what about from the sedimentary geology perspective, which many of you are world leaders in this field? So the DZ revolution is really about using absolute ages from sedimentary rocks, and this is in contrast to what has been done previously. Remember perhaps from your historical geology course that one of our founding fathers of geology, Nicholas Steno, was able to work out what we refer to as the 4 laws or principles of stratigraphy. You remember these? This was on exam 1, right? Superposition, horizontality, cross-cutting relationships, lateral continuity, the kind of laws that we use to do to work with sedimentary rocks. Well, what would it have been like if Nicholas Steno could have determined absolute ages from these detrital zircons? Do you think that he would have come up with a 5th law for dealing with sedimentary rocks that would be something like a sedimentary unit can be no older than the youngest detrital zircon grain? I think historical geology textbooks in the future might want to have a 5th law. This would be the law of detrital zircons. I'd love to have a conversation with you during the rest of the meeting and hear your thoughts about this. Do you think that we should come together as a community and see if we can establish this new law of how to use geochronologic data from sedimentary rocks? So let me talk a little bit about the future. This is kind of where we've been. I'm going to wrap up here in just a minute. The future, I think, is very exciting in this field. Do you think we're going to go faster and faster in the future? Yeah, that's inevitable. I can't imagine how we can go faster than we are, but of course we are. By the next IGC meeting, we'll be doing ages in less than a second, of course. Bigger data sets, more people doing these, more publications coming out. Here's a really exciting application. In the past, we have done pretty much 1 spot per zircon grain. If they look like the ones on the left there, no problem. Doesn't matter where you put that little yellow circle. It could be anywhere. You'll get the right age. But if you look at a group of zircons, about 10% of them look like that beautiful crystal on the right. We think this is kind of like a tree, that the oldest part of the zircon is in the middle and gets younger, younger, younger outward. But right now, we don't have any technique that we can use to pick apart the history of a zircon grain that's so complicated like that one. But we're working on that. We've just developed new techniques for doing age mapping. We dial the laser spot down very small. We raster back and forth across the zircon grain. And here's an example of one zircon grain that we've actually determined 3,400 ages from that individual crystal. Yeah, it took us 12 minutes, but stay tuned. It's going to happen a little bit faster. Within a few years, we'll be able to do this probably in less than a minute. I think this is the future of doing this kind of work. Instead of doing a single age from a crystal, we'll be doing mapping of these kinds of crystals and learning so much more from those analyses. I think Raman is an underutilized tool at this point. This is going to be revolutionary when we figure out how to do Raman analyses of zircons, combine that with uranium-lead isotopic measurements. This is going to help us produce more reliable ages from these crystals. We're also, with laser ablation ICP-MS and with ion probes, able to measure lots of different elements at the same time that we do uranium-lead geochronology. And so imagine as we get more and more of this type of information, we'll be able to look back in Earth history. We'll be able to talk about changes in crystallization temperature, thickness of the crust, oxidation state, all around the world, all back through geologic time, just by the information preserved within these tiny little crystals. And of course, one of the challenges for us, for all of us in this community, is having software that is able to handle the information that we generate. The information is getting more complicated, larger data sets. We need to be able to describe the data, visualize it, do statistics on it, archive that information in databases. And now, of course, the challenge is this software needs to be user-friendly. Non-geologists, non-geochronologists need to be able to use this software to handle their data. So those are some of the kind of future outlook for doing this type of research. I think I'm going to end here and just say thank you to the local organizing committee, our leadership within IGC and the IUGS, the conveners of these different sessions, the session leaders of all these different sessions. I think the IGC meeting has a spectacular range of topics that will be covered during the next few days. I'm so looking forward to sitting in these sessions with you and just observing sort of great examples of new instruments, new applications, new people, new voices, new software that's being used to do this kind of analyses. And I'll stop here and just thank you so much for the honor of being awarded the 2024 Argand Medal.
Please give another round of big applause to Professor Gehrels. proud recipient of Emile Argand Award. It was a wonderful